Okay, chemistry students, this is part 2 in our chapter 18 equilibrium instructional videos here. And we're going to continue our discussion about equilibrium, but then expand this into maybe some other types of equations to look at them. Okay? So, just a quick reminder from our last discussion in part 1 of this series that we are talking about equilibrium, and you should be able to write the equilibrium constant expression. And if you remember from our previous discussion here, we learned how to write that equilibrium constant expression using a balanced equation. Remember, the equation has to be balanced, and you have to have reached equilibrium, and then you can write the equilibrium constant, capital K. Don't forget that the coefficients become exponents here. All right? Also remember that at equilibrium, it means that the forward rate is equal to the reverse rate. It doesn't mean the concentrations of the reactants is equal to the concentration of products. It means the rates in both directions are equal. That is a general balanced equation, just showing you that the m and the n, the x and the y, all become your coefficients. Your exponents in the equilibrium constant expression. Okay? It is always products over reactants. Also, you should make note, you need to commit this to your memory, that this K value here, it does give us information about the relative concentrations of products and reactants at equilibrium. It doesn't tell us anything about how fast the reaction took to get to equilibrium. It tells us nothing. It does not tell us anything about the speed of the forward reaction or the speed of the reactions. It doesn't tell us anything about how fast it took to get to equilibrium. It may be a very, very slow reaction. It may be a fast reaction. That's not the job of K. It doesn't tell us anything about the rate of the reaction itself. That was last chapter when we talked about kinetics. Also, I need you to know that K is the equilibrium constant expression, but we could have a K value for the dissociation of an acid, and so we might write K sub A. That A just means for an acid, like a weak acid. Hydrofluoric acid, you put into water, it dissociates into the ions, H plus and F negative. Here would be the K expression for the dissociation of that weak acid. You might see Kb, which would be the same idea but just for a base. And the one we're going to look at a little bit more here is the Ksp. This is for when a solid dissolves. If a solid dissolves, then you might see the subscript Sp, stands for solubility product. Example, if you take silver sulfate right here, it is a solid, and you put it into water, it dissolves, it breaks apart into ions. It's going to break apart into its cation and its anion. You have to balance this. If you notice, there are 2 silver ions for every 1 sulfate ion. So this is going to break apart into 2 separate silver ions and a sulfate ion. When you write the solubility constant expression, we're going to write Sp for solubility product. Solubility product means you have a product of the solubility of the 2 ions there, or it might also say ion product. You do not put your solid into the K expression. Remember, you do not put solids or pure liquids into the K expression because their concentrations don't change. So you just put the concentrations of the 2 ions that are in an aqueous solution. This would be AQ. AQ. So, concentration of the silver ion squared. Why is it squared? Because to balance this equation up here, you had to put a 2 in front of the silver ion because there are 2 silver parts in the silver sulfate, and then times the concentration of the sulfate. This is your K expression for the dissolving of silver sulfate. This is called, right here, this is called the solubility product or called the ion product. All right? when we talk about solubility, solubility is talking about how much of these two ions can be dissolved in water. So solubility has to do with the concentration of these two ions when this is at equilibrium, which for a solution like this, it means it's saturated. This K value is called the solubility product for dissolving a solid. Solubility product, also called the equilibrium constant. Okay? So you are going to be asked to do problems where you're either given the solubility, which means you're given or can find these concentrations here, and you'll be asked to find the solubility product. Or you'll be given the solubility product, you'll be given this number, and asked to find the individual solubilities, or how much of the solid dissolves. So it's a simple equation. It's like y equals, x is the solubility of the silver here, but that's going to be squared, maybe times 2, and then this x is the solubility of the sulfate. So you'll see it's a simple equation that has just two variables in it. You'll see as we work it through. Solubility is usually measured in a certain number of grams that dissolves in 100 grams of water, just so you know. And for solubility product, if this product here, if the ion product, the concentrations that you multiply together, if that is greater than this KSP value, then you've put too much into the water, and not all of it's going to dissolve, which means you're going to see it precipitate. If this product of the concentrations is smaller than the given KSP value, that means it's all going to be dissolved, and you have not reached a saturation point yet, and there's not going to be any precipitate. Okay? So you'll be doing problems where you're given the solubility and you have to find the solubility product, or you're given the solubility product and you have to find the solubility of the different ions or of the solid. Okay? So really quickly here, let's just look at this as an example. So as an example, we have sodium sulfate. So sodium sulfate, and when you put that in water, it is a solid, you put it in water, it is going to dissociate into 2 parts of sodium ion and 1 part of the sulfate ion. Okay, right here you see that there are 2 parts of sodium for every 1 part of sulfate ion. So you have to balance this. That means when I write my solubility product, the equilibrium constant expression, it is the concentration of sodium squared, don't forget that coefficient there, times the solubility of the sulfate ion. Okay? Now, let's say that they tell you a certain amount of sodium sulfate dissolves. Okay? So let's say you've got your sodium, let's do it here. Sodium sulfate right here. For every 1 unit of sodium sulfate, you are going to have 2 sodium and 1 sulfate. Okay? So if X amount of this dissolves, then you're going to produce 2X of this and X of the sulfate. So that means if they give you a number, X, whatever that X is, this amount here that is dissolved at the saturation point is 2X, and this amount is X. So let me just rewrite this right here to show you how simple the equation is. This K value, let's say it's just Y. This concentration here is our 2X, and you're going to square that. And then the concentration of the sulfate is just the X. So you can see how this equation becomes just a 2-variable equation. Even though we've got 3 things up here, it becomes a 2-variable equation. And like I said, either you're going to be given this X, and then find the y, or you're going to be given the y and have to find the x. Okay? And we'll do a couple right here, right now, just so you can see. In number 1, on all of these problems, you have to write the dissolution equation, or the dissociation equation. So you got to take this. These are all solids, by the way. So none of these compounds are going to be in your K expression. These are all ionic compounds right here. This MgS is going to break apart into Mg ion and sulfide ion. So your KSP is concentration of Mg ion times the concentration of the sulfide. This is balanced, so there's no exponents here. Zinc nitrate, that's going to break apart into the zinc ion. And if you don't know these ion charges, you're going to have to remember how to find them. And 2, there's a 2 right here. It's hard to see, but there's a 2 nitrate ions. Nitrate's a -1. So this KSP value, or expression, is going to be zinc, concentration of the zinc ion, times the concentration of the nitrate ion, squared. Apologize for how messy that is. Okay, so you try these and see if you can figure out how to write both the equation, the balanced equation, and the KSP value. All right, and let me just show you really quickly here how to do one of these, and then we'll do the rest of them in class. So this is saying you have this amount of lead fluoride that dissolves in water, and it's asking you to find the KSP value. So again, you have to know how to write the proper dissociation or dissolution equation of lead fluoride. When this reaches saturation, you are going to have a certain concentration of lead ion.
All students and parents will need to vacate the building at this time.
And you will have a certain concentration of the fluoride ion. Don't forget, there are 2 fluorides for every 1 lead, so you have to balance that. Your KSP now is going to be the lead ion and the fluoride ion squared. Okay? This number right here is how much lead fluoride dissolves. And that's going to change, and it's going to produce the same amount of lead ion, but 2 times the amount of the fluoride ion. So you have to make it double here because of that 2 right there. So you can see this KSP is going to be, the lead concentration is the same as the given amount of the lead fluoride that dissolves. Let's put just an X there for right now. This fluoride is going to be twice, and it's squared. That's terrible, sorry. Okay, that's X times 2X quantity squared right there. Now you take this number right here and you put it in for x, put it in for x, and find out what your KSP is. Okay? Again, I apologize for it being so messy there. We will do some more problems like this in class. I just wanted to get started so that you could better understand a little bit about the solubility product. All right, nice job.